Good afternoon, good evening to everybody that has joined this edition of ISTAT Learning Lab. We are very pleased to have another discussion with some eminent professionals here on a new technology that is going to be impacting, our industry in the years to come. I'm very pleased to introduce Mark Page and Warren Willits from JetZero as they embark on their journey to net zero. Very, very lame joke, sorry. Anyways, Mark is the founder and CTO of JetZero. He is the Chief Technology Officer. He started his career at McDonnell Douglas, where he was the technical program manager, sorry. He led engineering for a 3-year NASA-funded initiative to investigate the blended wing body, BWB potential. The groundbreaking research led to the BWB concept being embraced by the aerospace industry as a viable path for future airliners and to subsequent research at NASA and elsewhere. Mark co-founded the DZYNE Technologies in 2012, where research into a new BWB concept continued with NASA partnership. JetZero was spun out of DZYNE to take BWB concept from R&D stage to the market. Warren Willits is the president and CEO of Jetstar Partners. Warren has played an active role for JetZero as strategic advisor since its founding. He began his career as a sales director at McDonnell Douglas, and after leaving Douglas, he became actively involved in the leasing industry, spending more than 20 years managing and marketing leasing portfolios. Today, he's founder and CEO of Jetstar Partners, an aviation consulting services business for commercial aircraft and helicopter lessors and operators. Warren had been an active ISTAT member for 30 years, and he previously was on the ISTAT board and ISTAT Foundation chair. Welcome, gentlemen. Thank you for being with us. I will leave you to make the presentation on JetZero. Before that, I would like to remind our audience that they can post their questions on the Q&A button at the bottom of their Zoom screen. And after the presentation, I'll be happy to put these questions to the eminent gentlemen for their answers. So, Mark, Warren, round is yours.
Good morning, everybody. And thank you, Mamoon, and everybody at ISTAT for this invitation. It's really fun to share what we've been up to with the broader aviation community. And I think this community in specific has obviously is very knowledgeable in everything airplanes and the market of the airlines. And I think we have some really relevant stuff to share. The big thrust of this airplane is efficiency. And we're getting this efficiency with an entirely new configuration. And I'll tell you a little bit about why the configuration has the shape that it has, and how can it possibly produce the savings that we're seeing. But the preamble is this: we've been working, the aviation industry has been doing a great job reducing fuel consumption over the decades. And the interesting bit is that if you go back to 1950 and look at the 707, the first biggest successful program right after the de Havilland Comet, which was the first jet airliner, this species was formed: swept wings, potted nacelles, cylindrical fuselage, and an empennage. And as you see, over time, that hasn't changed. The species of the airplane hasn't changed. Most of the benefits you see on the left were actually engine-related benefits. So what can we do? Well, we have a proposition with this airplane to achieve a 50% reduction in energy consumption, and that goes along with the 50% reduction in CO2 and water vapor products as well. 50% is a bold statement. That is saying a lot. And hopefully you will see, as we share some of this work, why we feel so bullish about the technology, why the folks at NASA and the Air Force have, after vetting our work, also see these benefits in the future. And I'll start with talking about the structure of the airplane. Let's look at a tube and wing. And on the top, I'm showing the lift carried by the airplane. On the bottom, I'm showing the weight distribution. And you'll see that I'll just mention that if the blue and the yellow were equal and opposite, wingtip to wingtip, then in theory, you don't need structure. Everything will stay in its place. Of course, you do need structure because those shapes change over time. But nonetheless, the amount of structure I need depends on how dissimilar those shapes are. Any place where the weight is concentrated and the lift isn't lifting it and canceling it is going to make big structural bending moments, as we call them, and the shear stress. And that results in the need for thick skins in the wings and big webs. The airplane, of course, with the tube and wing, there's some what we call carryover lift on the fuselage, but the fuselage itself doesn't make lift, so it distorts the shape of the lift distribution. The blended wing solves that by simply being continuous airplane airfoil from wingtip to wingtip, and we also distribute the mass in a very favorable way. And when we do that, the stresses on the airframe from wingtip to the middle are much reduced. The airframe can be very, very light. But there's another part to the blended wing story, and that is this. If I look at a tube and wing airplane above, and clearly the fuselage carries the passengers, the engines make the thrust, the tail keeps it stable. By the way, why does the tail keep it stable? Because cylindrical bodies are profoundly unstable. That's a huge disadvantage of tube and wing airplanes. They need a giant empennage to compensate. Nonetheless, if I take a look at the airplane that we've evolved, it's been a very successful configuration, very successful species. One of the things you'll notice is I've got rather slender wings. I've got a big, deep fuselage. And that wing, its slenderness is limited. I can't just make it longer and skinnier forever because it flexes too much. It becomes not a strength problem, but a stiffness problem. So the outer wings on airplanes today have gotten about as long and skinny as they can get. What the blended wing does is this. It changes the fuselage into a lifting shape to continue that lift from wingtip to wingtip, pushes those slender wings further outward. Now I have significantly less drag due to lift. The interesting thing about this market space, as most of you are extremely familiar with, if I looked at the worldwide global fleet and plot that against the capacity of that global fleet in seating, you get a really interesting curve. Dark blue is single aisle aircraft. The lighter blue are twin aisle aircraft. And you've got this interesting discontinuity somewhere around 170, 180 passengers. Well, what's going on? Well, the first thing that has to be said is in the middle there, those airplanes are in the process of vanishing. 757s, A300s, 767s, those airplanes and airplanes in that range and passenger capacity haven't been introduced as new aircraft for decades. And so it's created what we call the mid-market gap. The airplanes that are still in the fleet today will soon be gone in that area that I just showed you there, about around 210 passengers or so on the other side. So that is the so-called mid-market gap, and it's created this giant spike in demand for everyone trying to get in. Yeah, so everyone's buying the beachfront property, but they can't get into the pool. That's the gap that we intend to address. And we believe that that demand is going to be extremely high once that market gets served again. But as you know, the mid-market gap has a couple problems, presents a couple real challenging problems. One of them is that since no one's been working on new aircraft for that segment, no one's also been working on engines in that segment. So we have on the left a traditional narrow body engine. Maybe it gets up to 34,000 pounds of static thrust. And on the right, the next closest engine is about twice that thrust. A modern engine available today is about 64,000 pounds of thrust. And there's a gap in the engines then too, and that has been a barrier to the OEMs introducing the so-called mid-market airplane. They would have to make a new airplane and a new engine. What we've done with the efficiency of the blended wing, we've reduced the demand on the engine to about half of what it would be for a mid-market airplane that's a tube and wing aircraft. When that happens, suddenly the advanced LEAP and Pratt & Whitney GTF engines are perfect fits for us, perfect fits for this mid-market mission. And that problem is now gone away. I can have off-the-shelf engines that are mature and getting even more mature, available to serve that market. That's a big change in what it means to the world. The airplane is going to be very conventional in some ways. In other words, how it fits into the market, well, it's going to fill in space that's been long empty, but it's just an airplane. It flies around 8/10 to 0.84 Mach. It's going to have typical mid-market ranges and typical mid-market capacities. And when a pilot jumps into it, strangely enough, though it looks different, it'll be very familiar to the pilot. The displays, the controls, the procedures are all going to be the same. Jetways, ground equipment, all that stuff will be the same. So when we bring an airplane like this to the market, what do we think passengers are going to say? What's going to be the reaction? We've been working this for a long, long time. You can see on the bottom left that that's what the airplane looks like. If I were to take a slice wingtip to wingtip down the middle, you can see that the airplane's built out of 4 bays. Actually, each of the bays that rib between them has apertures, so you can actually see left and right beyond that. It's a very great sense of space. Skylights in every bay. And on the right, you can see the general layout and passenger flow and service crew flow through the airplane. The remarkable thing with this airplane, of course, the payload is wider instead of long. And I enter there about midway through the airplane. I enter on the left, and I have not 1 aisle to go down, I have 6. And when you think about what that's going to do to loading and unloading time, it's a dramatic improvement. We often get questions about emergency egress, and that's a great question to ask. We have 6 major exit doors on the airplane at the top, very much like a competing tube and wing aircraft. Most tube and wing aircraft also have perhaps 2 doors over wing. We don't need over wing, so all the doors, everyone will exit the airplane without having to climb up and climb through a window. Every exit is a door. And because we have such a short main cabin, look at that, it's only 12 seats long. That means that the time it takes to load, unload, or make an emergency evacuation of the airplane is much reduced. And everything that you can measure related to how people move around in airplanes, what's the average boarding distance, how many seat crossings? Seat crossings are the things that slow you down. And how far am I from the emergency exits? And so on average, we have very significant improvements on all of those things. Research by in England with a full-size, much larger blended wing body concept was declared the most aggressible airplane ever tested by Cranfield University. So there's a lot to recommend the airplane in terms of emergency characteristics and qualities. Let's dig a little deeper into this fuselage question and how the fuselage is constructed. If I look here, class leading A220, lovely interior, and it's, I think, the favored interior of all aircraft right now in ratings. We're, of course, doing something different. We have vertical sidewalls. We're looking at a 4 abreast seating arrangement. Our ceiling is higher, and look how much further out and up I can put the luggage compartments. So now the clear way for you entering and leaving the airplane and putting your luggage up there, and for the staff on the airplane, is it's a much more usable open space. let's see if, there we go. So the airplane, again, looking at the total cross-section of the airplane with these individual bays, 4 abreast seating. The beauty of this arrangement is that there are multiple benefits, but the vertical sidewalls allow us to add over 50% more overhead baggage volume, which means that anything you bring aboard, there's room for. And with the 4 abreast seating, we can actually assign half of the rack above your head to you and your seat number, and the other one to your partner there. Everyone gets a seat, a dedicated baggage storage space on the airplane, numbered to your seat. So Shape enables so much. This new species, this new shape of airplane is opening up not only things related to climate because of the efficiency of the airframe, and we'll talk more about how quiet the airplane is, but we're also going to be making a major step change in comfort because the sidewalls are vertical, the bag racks are much further from the seated passengers. They have much better head clearance, and they're very accessible from the center aisle. The 4 abreast cabins are wonderful, no middle seats. And then in terms of operating cost for the airlines, this efficiency obviously is going to have a significant advantage. But not only that, we are providing a path to zero emissions with liquid hydrogen. This work has been studied, blended wings, for a long time. I was there at the birth of the modern blended wing. Flying wings have been around a long time. This isn't just a flying wing, it's a very different thing. But it has, there's also been other antecedents that have been out there that presaged where this was going. But the actual blended wing that we're talking about was created in 1990 by the folks here. Bob Liebeck was the first person to pen the general concept of having a concentrated payload compartment that was concentrated not more so fore and aft and widened, and what that could offer to the airplane. Many years ago, when we were all a lot younger, we were flight testing the airplane concept to evaluate its stability characteristics, and we did so with NASA sponsorship, very successful test program. And that has led us to this blended wing airplane that offers fuel efficiency. But the surprise was all the other things that it offers. And this is a good example. When I look at conventional aircraft with the engines mounted in front of the wings and below, when I'm taking off and landing with my flaps down, the bottom of the wing and that flap focus the noise on the people below. With the blended wing, the top-mounted engines, virtually no forward-radiated noise gets to anybody. That's all reflected up. And the jet noise is not being amplified by a flap presence when it's reflected down. We're seeing a huge reduction in noise, 30 dB overall reduction compared to a tube and wing, and 40 dB below the new stage 5 limits. So why are we saying 50%? Haven't lots of studies in the past shown that a blended wing is worth maybe 30%, but often 20%? Why are we claiming 50%? What's different? To get a change, you have to make a change. The change we made from the historical blended wing that I first worked on back at McDonnell Douglas with my colleagues was to go to what's called the single deck. The original blended wing on the bottom on the left, we had a double deck. The lower deck carried cargo, had leftover space to put the landing gear. But we wanted to make an airplane in the mid-market that was smaller than anything we'd looked at in the early days of blended wing research. And we wanted an airplane where we could remove one bay and make the airplane smaller to be a true single aisle competitor and be efficient in that space. But this created a problem. If I wanted to have an airplane with no lower deck, where do I put the landing gear? So in the darker blue, you see a traditional tricycle gear on an airplane. And what you see is that the main gear are pretty darn close to the center of gravity, the center of balance of the airplane. And that allows the airplane to rotate nicely and easily for takeoff. So I could pitch the aircraft nose up, get the lift I need for liftoff, and I could do so by pushing down on the tail surfaces with a modest amount of load. Now that works great for an airplane that is a tube with a long tail arm. So that's more like, pushing down on your lawnmower and making a turn. What if you had to push down on a shopping cart to make the turn? That's tough. Well, with a single deck airplane, that's what we had created. We moved the landing gear aft. Why would we move it aft, you ask? Well, it was an empty space, unoccupied. That's cool, but it's not the right place for kinematics of takeoff. We had to have something to address that. The other thing was that moving outboard was not possible because of the airport limits in wheel track. So to stay under the 9-meter limit and be qualified when we shrink it as a single aisle aircraft mission, we couldn't have the landing gear outboard, and it actually wasn't very efficient to stuff them there because it was stealing beautiful, irregular volume that's useful for fuel. So we moved the gear to the back. We had to add a trick, which I'll show you. The trick is this. The main gear and the landing gear are linked. They have a simple mechanical link. Could be hydraulic, could be cables, could be anything else. But when I pitch the airplane is free to pitch about its balance point. The airplane can't go higher or lower. The landing gear resists that. But once I unlock the landing gear, if the pilot pulls aft and there's airspeed, the nose will come right up with a very low download. And then something interesting happens, which is that we unleash the benefits of the body for takeoff and landing. And if you take a little look at the little picture of me on your screen, I'm going to show you something here. Oh, this won't work very well. I apologize. I just realized that that the background filter is going to prevent me showing you that. In any case, if you have an airplane with a big triangle in the middle and you pitch it up, that triangle of airfoil becomes my high lift system. I don't need flaps. I don't need slats. All that stuff I get to throw overboard. And a light load pushing down on the wingtips at my ailerons plus elevators, can do the trick to rotate the airplane. The other thing folks often ask about with this airplane is, whoa, your winglets look like fins, but they're so tiny. How does the airplane fly straight, and how do I turn it? And so if you look at the top, you'll see that we have an airplane which can create a very large yawing moment left and right by opening the controls. Instead of making drag like this, like the B-2 bomber on an outer wing control, we do it like this. It's a very quiet and, from a control standpoint, linear, smooth way to make drag. If I do it on only one side of the airplane, I can yaw the airplane for crosswinds. I can yaw the airplane to compensate engine out. But the full span controls also allow me to do ride smoothing and all kinds of gust alleviation. And because we have made them into small segments, we can control them to do much more than you've ever seen before on an airplane. We have flight controls across the whole airplane span. So gusts and turbulence and all those things, the flight controls can reject those excitations very nicely. In talking about flight controls, remember I mentioned how unstable fuselages are for tube and wing aircraft. Well, the empennage is what compensates for that. We don't need any of that stuff because we don't have this big cylinder that's so unstable. But as I said, we also don't need slats or high extension flaps. All those rollers and jack screws and differential sensors to make sure things are symmetric are just gone. All the failure modes are gone. The cost of it is gone. But in addition, we don't need spoilers because we don't have high extension flaps. We don't need the spoilers to dump that lift when we take off and land. So we're in a very great position for an efficient airplane. Now, the Air Force has taken interest in this because of its range possibilities. And if I look at what that what they would like to look at is, hey, they want to get into Pacific range performance, which is really not very easy to do today. And so we've prepared for the Air Force an estimate of what this airplane could deliver, and it's remarkable. So I can double the range of the best tanker out there right now, which is the KC-46. I can double the offload of fuel at a common range or radius, or I can double the radius at a common offload. So this is what has brought the airplane front and center to the Secretary of the Air Force, Frank Kendall, who, along with the Air Force, broader Air Force team, selected us to develop a prototype of the airplane that is actually going to be a commercial jet transport. So they're actually funding us to make sure that we're successful in getting a commercial launch of the product. That award is nearly $250 million, and it's going to result in 2027, the first flight of a full-scale manned flight demonstrator that can do the mission of a 767 or a small 787 with single aisle engines. And that's going to be a very exciting program and is going to be very definitive proof of these performance claims. The airplane in many ways is going to be just like any other airplane. We're still going to have belt loaders. We're still going to have the lift loaders. We're still going to be using LD containers, LD2s, LD3s, and so forth. And so as far as the operator goes, it's just another airplane. We do have left and right instead of fore and aft loading compartments. But otherwise, that's it. That's the difference. So we're blessed to have a fabulous group of young people and experienced people that have joined our merry band. If you look at the top, the advisor team we have is just absolutely stellar. And we're just so pleased that they're on this team. You'll see some newer faces below, relatively newer. Perhaps me, there's a couple, 4 people that aren't as new. But we've got some great mid-career folks who've come aboard who want to really do something different. They want to have a career shift that is meaningful for the global health of our planet. So what we're looking at is a multi-mission platform, one that can be a jetliner, a strategic tanker, and also a commercial freighter. And once again, it is something that will replace all the airplanes that are vanishing in the middle, that will be soon completely gone, large 767 size. And that's going to allow us also, because of the way the airplane has such usable volume, we're able to take the airplane, and in the future, when we get to liquid hydrogen supply being available, we can change the airplane by devoting 2 of the bays to that high volume liquid hydrogen, 4 times the volume demands of the same energy of Jet A. So you really got to find a lot of volume, and a blended wing delivers it. And then this 255 passenger, 5,000 nautical mile airplane becomes a 180 passenger, 4,000 nautical mile airplane. So it's a very capable jetliner in its own right, and far greater performance is achieved than any of us have ever heard of for turbine wing aircraft that are struggling to find a way to incorporate that extra volume into the airplane because the fuel can no longer be in the slender wings. I'd like to thank you very much for your time here. And I see do I actually have 10 minutes left over? I think I might, but I'd love to take your questions.
You actually do. You actually do. That was very efficient and very interesting. Thank you very much, Mark, for that. We do have a couple of questions that Warren has actually answered on the chat, but maybe Warren, you may want to take them online and discuss them more in detail. First one is on Airbus, I mean, because on the graph you showed earlier with
Sure.
the big gap in the middle section, someone pointed out that Airbus of the A321neos, they've sold quite a bit that are in the 200 plus C 240, 244. So if you want to comment on that.
Sure, no problem at all. So as I mentioned in the chat, the Neo is a fantastic airplane. Airbus has done a phenomenal job with the 321 from an aircraft that was not particularly well respected at one point in time to an amazing airplane today. So they've done a phenomenal job with that airplane. It's the same engine, obviously, that we're talking about with our aircraft, so we know that particular situation very well. But the 321 is being pushed to its limits. I mean, obviously, at 240 seats, it's in a max capacity configuration. It will not do the range profile that would be needed for much of the mid-market requirements. So it's again, it'll fill certain market sectors extremely well, but really it's on the bottom end of the mid-market requirement. And so obviously we're going to be pursuing both the upper edge of that whole situation, plus all the smaller wide body configurations for the range between 3,000 and 5,000 nautical miles.
So why aren't Boeing or Airbus building this? I think I think there's so many reasons they're not, especially that are internal to each OEM. But if you want to give a short answer, please, because we have quite a few we would like to go through. Yes.
So the short answer is very simple and in some ways very obvious. The Boeing and Airbus are still deriving value from their current products. And that's evidenced by over 10-year backlogs on their 737, A320, and 21 lines. 10-year backlogs approaching $1 trillion worth of value. So that's the shortest, simplest answer, because this airplane is competing with that. And that is money in the hand if they, if we all get there. And it just is not a compelling business case for them to change horses. Both Boeing and Airbus have had blended wing programs. Both have seen great gains. I will tell you that what we've been doing is very different. Starting in 2012, we started doing research at the company, Design Technologies. Apologies for not telling you about how to pronounce that crazy name, Design Technologies. And we received NASA support because they were very intrigued by this pivoting gear concept that allowed a single deck airplane to emerge. And the reason for that was they'd invested all this money in blended wing research, but it only worked for very large airplanes. And when we got a single deck solution with our landing gear, they were super excited because suddenly the value of that research to the nation was doubled, because the worldwide fuel burn is split about 50-50 between twin aisle and single aisle aircraft. So suddenly this technology has value to a market that no one else has been able to fit it into. We can go all the way down to 110 seats and still have tremendous performance gains. So in any case, it's that's a question we get often. The other thing that you should probably say is, ask them, ask them why they're not pursuing it. But that's an awful lot of backlog that they have to protect.
To speak about certification, how does the design meet the single engine out certification requirement? I have to admit, I have no idea what that means. So
yes, this is a Part 25 airplane, and it's funny. In my early career, it took me a while to realize that there's no such thing as a single engine Part 25 airplane. Part 25 presumes engine redundancy. It doesn't even speak to the possibility that one day there'd be one engine that somehow could do the job. So it's built completely around the premise that at any point in a mission, I could lose an engine. This tends to be most critical, of course, in takeoff, less so on landing. But in takeoff, I have high thrust. If I lose an engine, big stuff happens. All of today's airplanes demonstrate in flight test and certification that engine out condition. They look at making sure that the airplane, when it suffers an engine failure, and maybe it's on a slightly degraded friction runway, maybe it's wet, that the airplane doesn't depart more than 30 feet from centerline in the recovery. They make sure that under no conditions with the engine out, if I rotate, that I haven't achieved enough speed to lift off and start moving away from the ground. We do all those things the exact same way. So it has, the thing that is interesting, I will tell you about the airplane, is that since we don't have those high extension slats, with slots and rails, we don't have high extension flaps with slots and rails. The drag of the airplane in takeoff is minuscule. Once the gear comes up, it's in flight configuration. There's no other configuration change. So what we're seeing is that compared to most twin engine airplanes that are very second segment critical, what that means is that the pinchiest bit of the takeoff with an engine failure is not controlling the ground and not controlling the air. It's, do I have enough climb gradient after that engine failure? And that is measured in the so-called second segment of the takeoff after liftoff. And there's very stringent requirements for that climb gradient. Because we don't have flaps and slats hanging out in the breeze, the airplane is so clean that frankly, the airplane with the gear down is about the same efficiency as a tube and wing with the gear up and clean. So we're showing really great climb performance. That's not even an issue. And now we can get a big takeoff performance improvement because we're not restricted by the climb performance. We have so much lift to drag ratio. The climb is not the pinchy bit. Now we can make the airplane more optimized for takeoff. And as we've done that, this pivoting gear and the configuration of the airplane allows us to have at least 25% less takeoff field length, sometimes 40% less takeoff field length than tube and wing in the same mission, and 25% less landing distance. You might ask, well, how does 25% less landing distance come about? You're just on approach, you touch down, you hit the brakes. Well, the landing gear we have is, we have a 3-point landing gear. Center of gravity is like a third of the way up from the rear main gear forward. All 3 bogies are carrying about the same load. So we have to have brakes on the nose. So the left main, right main, and nose gear bogies all look the same. The trucks are the same. The brake stacks are the same. And I can use them for braking. People have done nose wheel braking very rarely. But on this airplane, with that nose wheel braking, because the nose gear brakes so effectively, if you think about your car or a race car, you hit the brakes, you have the so-called weight transfer, you feel the car surge forward, it moves the vertical reaction to the ground forward. So your front brakes do most of the work in a car. And when I'm braking, I can still turn. Works just fine, always has. So by harvesting that weight transfer forward, the most efficient braking you can ever get is at the front. We're getting a third more braking effect than anybody else with the same rubber, same asphalt, same brakes. The free body diagram gives us a third more braking, and that helps take off field length as well as landing.
Thanks, Mark. As I said, questions keep coming in, so please, having questions is always the most important part, interesting part of this learning lab. So that's why we're here. Is there a scalability element in the design of this aircraft?
Yes, there is. So Warren will know that I'm looking around for our other model. Someone has moved it. So when we were first developing the blended wing in the 90s, Bob Liebeck and I had just gone to visit Mac Air in St. Louis. They were our sort of the parent half of McDonnell Douglas. And we were doing a review with their team of technical experts. And someone said, well, don't commercial airplanes don't tube and wings have a big advantage because they're so easy to stretch? I just put another little piece of cylinder in front of the wing and behind the wing to keep it all balanced. And now suddenly I go from a 180 passenger to a 210 passenger. Isn't that a big advantage? And it is. That is an amazing thing. And in so doing, one airplane can serve many more markets than it was first certified for by plugging it. the problem has always been that when you plug a tube and wing, the wing doesn't change. Now, you could change the wing, but that's a lot more expensive to get a derivative. And typically that's not done. When I grow the airplane with, let's say I stretch the airplane and I go from 180 to 210 packs. When that happens, obviously as takeoff gross weight has to go up. I'm going to need bigger brakes and bigger, everything gets a little bit bigger. And the structure, though, only has to be modified in a slight way. Usually we do acid chem milling of the skins of wings on traditional aluminum airplanes. They just mill away a little bit less. And you design it in advance. So where ribs meet the skin, where spars meet the skin, I'll never touch that thickness, but I'll allow material to be added in between where it's easy. So I can use the same tooling to build the wing, and suddenly the wing has 10% more lift capability. So what happens though, so what I've just described is I can put plugs in front and back of a tube and wing aircraft, add capacity, and keep it balanced. I can add wing gauge thickness without affecting the tooling virtually at all. So now I've got an airplane that can do more in terms of capacity, but it can't do more in terms of range. And that's really tough. And its efficiency has diminished, and its takeoff field length has been impacted terribly. So what we've done is we have a means to improve that, to answer the question that was put to us by the folks at McDonnell on takeoff and growth of the airplane. How are we going to take this curvy shape? Where can I put a plug into it? How could I possibly stretch or grow the airplane? Well, the answer came to me on the flight back from St. Louis back in 93 or something. It was what we call a T plug. Now we call it a Y plug. Basically, we do the plug on the center line, not fore and aft. If I were to cut the nose off the airplane and extend it forward and connect the dots back, obviously that's an airplane with big discontinuities. But if I take the nose off, split the airplane down the middle, put a plug down the middle, and a little collar at the top to remate with the nose, which I keep unchanged, and the outer bit is unchanged, suddenly I'm adding floor space for more payload. I'm adding wing area because it's a flying wing. And I'm adding high lift even faster because it's so much center body. And I've added wing span, so the aerodynamic efficiency, the lift to drag ratio, is almost constant from 110 packs to 350 as I stretch the airplane with the exact same cockpit, exact same outer wings, exact same hydraulics outboard. It's a very significant feature of a blended wing that actually it's not hard to stretch. It's fairly straightforward to stretch. You have to respect certain constraints. And when you do it, you get an airplane that stays balanced, has the right lift, the right max lift, and the right L over D across the whole mission space, despite the fact that you've shrunk it or grown it. For that same reason, you've probably all heard about how bad tube and wings get when you shrink them. And that's true. The weight per seat, it goes up, the fuel efficiency goes down, things get worse because it's overwinged. Now you have the opposite problem. You have too much wing on these small airplanes. For us, we're taking wing out when we take passengers out, and it keeps that balance really, really well.
Thanks, Mark. We have another one from Dominic. Suppose you succeed in building the prototype that works. What then? How do you stand a commercial mass manufacturing capability? Or do you just sell the technology to Boeing or Lockheed?
Good questions. Here's what we always say: the politic answers. We'll listen to anybody. We're not going to. We'll have talks with anybody. Certainly, the intention is that this is a classic disruption, and it's challenging, and some argue impossible for large successful incumbents to embrace a disruption this big. And so whatever the path is, we're totally working as if we're going to do the whole darn thing. And that's why it's so important that we have these partners aboard that are going to help ensure that we can put that realization together. And these partners are helping in a lot of ways. Not only do they make certain things that we need and have certain expertise, certainly a company like Northrop fully understands scale, how do you go from a prototype to production, serial production. And our other partners have similar skill sets related to how they can ramp production to support different things. So right now we are working as if we will not be acquired. We're not saying no to that, but we're working as if we're not, because we're going to keep going. It's important to point out too that the prototype is giving us a 2-year jump on developmental flight test, which is just hugely valuable. But in some ways, it is not a gate to produce the airplane for the commercial market or even the military market. Whatever happens with our demonstrator program, we're on the way and we're doing development for the real airplane fully in parallel. So it's all go towards a commercial product factory. We're already going to the green fields. We're already talking to the governors and the senators about finding out how much they would really like us in their neighborhood. So that's the stuff you got to be doing if you're going to do something ambitious like this.
Yeah, absolutely. Mike and Warren, very fascinating design, great work. I was wondering if you can talk about a little bit about the challenging of using liquid hydrogen in terms of sustainability. What is challenges of using green hydrogen?
Right.
I think that's the case for JetZero and other new aircraft prototypes.
So we didn't talk about SAF. I didn't talk a great deal about liquid hydrogen. SAF is sustainable aviation fuel. You're probably familiar with the fact that it's derived from biomaterial, bio waste, or plants like corn or switchgrass or whatever. And we take that and use the carbohydrates to create a synthetic fuel. And then that synthetic fuel gets certified just the way Jet A gets certified or other mixes get certified for use in aircraft. Meets all those lubricity properties, meets all the temperature things, all the fungicidal properties are all there. And the problem, of course, is that that's a longer path to the product than just drilling it out of the ground and cooking it up a little bit. So SAF is interesting because the concept is I'll burn this fuel, which doesn't look much different than Jet A, actually, and I'll throw just as much carbon dioxide and water vapor into the atmosphere. The difference is the next time I go get some gas, it will have come from a plant that sucked up some of that carbon dioxide in the process of growing. And that's the principle of how SAF works. That said, it's not 100% efficient. In fact, it's lucky to get 50%. It can't be called SAF unless it's at least 50%. And the folks working on it right now are challenged to demonstrate that 50%. Nonetheless, it does say that if I had 100% synthetic fuel, SAF, on the airplane, in theory, that alone would reduce my carbon dioxide emissions by half. Obviously, all of that helps us even more. If the world makes SAF, wonderful, we'll go use it. An interesting factoid is that if I take a 767 today, or a very small 787, to power that with SAF takes a land area, arable land, with a single growing season equal to 2 Manhattan Islands. That's how much land you need to make the sustainable aviation fuel just to keep one 767 airborne. And it gives you a sense of the scope of this problem. SAF won't get us all the way there, may not get us even close. Hydrogen is probably the way to go, but hydrogen doesn't come for free either. And so this discussion about the ways I make hydrogen, blue hydrogen and green hydrogen, is really important. Fundamentally, if you have to have that hydrogen made either with solar, geothermal, nuclear, wind, if you do it that way, you're going to get minimal side effect carbon dioxide, and you'll have something that is really sustainable. If you don't do that, then it's true that it's hard to actually make get a benefit if you don't actually have a completely net zero energy source to make the fuel.
Yeah, indeed, a lot of challenges ahead for our industry.
Yeah, I'll just mention also the fact that we are definitely have hydrogen in the long-term strategy for the airplane, but we're going to wait for the market to dictate exactly when that occurs. It's not going to be something that we're going to push forward until the market shows the fact that it's capable of supporting the hydrogen.
Right. The way we look at it is we're going to reserve that option. We do think it's going to come one day, but until it comes, what we want to do is deliver 50% fuel savings. Still do our part to improve the global situation and the economics situation of airlines who are going to be operating these modern airplanes with these modern, more costly fuels.
And the other comment I'll make also is the fact that this airplane truly is the only real designed airplane for hydrogen at the end of the day because of the width factor, the benefit of the width. And so when hydrogen does become viable, then this profile will be the platform that hydrogen will be used.
Good point. Thank you. How do you ensure consistent and stable separation on the lifting fuselage in a crosswind? And also when the aircraft stalls, how do you ensure the airflow into the engines is uninterrupted? Yeah, sorry, interrupted.
Those are great questions. Blender wings are funny things. They're kind of surprising. When I was at McDonnell Douglas, we merged with Boeing. It became clear that Boeing had limited interest in blended wing, and I went off and lost my head and went into open wheel racing. And then in the open wheel racing guys, we did some cool stuff. We tested in wind tunnels, did all that kind of thing. Then they said, "Hey, wait a minute! Airplanes. Maybe we can get into this drone business," which we did. And we were had the first blended wing drone in service in Afghanistan and Iraq through Northrop Grumman, who fielded the system. But we got to test that airplane like crazy, beyond this testing that we had done even before at Douglas. And one of the things that happens that immediately becomes clear is this center body never stalls. It just doesn't stall because you're not stressing it enough, because the center body doesn't have a neighbor just as fat as him stressing the air just as much as him. If I don't have those neighbors right next to me, like a normal wing that's long and skinny and lengthy compared to its chord, then it's just not stressing the flow. So what we're seeing in all of our work is that the flow properties into the inlet are quite pristine all the way through wing stall. Where is the wing stalling then? Well, it's stalling near the pinchy bit. If you look at the image behind Warren and I, you'll see that there's where the slender wing mates to the larger center body. That's where it stalls, and that stall pattern never makes its way into the engine. We have to go about 15 degrees past maximum lift to get any muck into the engine. So that's the first thing to be said. That's also the reason why we're able to rig the engine so intimately with the airframe and hide a bunch of the skin friction drag that the bottom of the nacelle would have, that a pylon would have, that the shadow under the nacelle would have. We get to throw all that drag and weight away, but we do require a diverter to keep the flow that's just normal, not even separated, but just has lost energy, to divert that. So we have that. So the other question was the stall characteristics and the crosswind.
Yeah.
So the stall characteristics, we design the airplane so that the wing stalls first in the middle, and then the stall does progress outboard and inboard after that. And so what we're using, we're using the same technology that everyone uses today in their envelope protections. So fly-by-wire airplane, we have angle limiting, bank angle limiting, all those things, so that we never have to, we will never find the airplane in a place where I've had that, just what I described a minute ago, going 10 degrees past stall, and now the separation has grown inboard and becomes substantial. Crosswind is interesting, and crosswind decrab. I've received this question a couple times, and I conclude that it seems like it could be a problem to people when they first see the airplane. It isn't. It's actually the reverse. But let me describe that a bit. So the B-2 bomber, flying wing airplane. That airplane, when it comes in and does a landing with a crosswind, right? When you're doing the landing, your nose is pointed into the wind, but you're tracking right on the straight runway. So your nose is pointed that way, but you're tracking on a straight runway. And then right before you touch down, you got to decrab, line up. And once you decrab, now the wind is going to blow you off. So you have to at the very last moment and then touch down. What blows you off when you decrab and get parallel to the runway and now the crosswind is just pushing against the side is the side area of the airplane and your giant fin. That is what's pushing you off the center of the runway. That's what requires very large roll input to push the windward wing down to get a gravity component to fight that force pushing you off the runway. And that's why crosswind decrab is a big deal on tuba wing airplanes. I got a big side area with that fuselage, and I got a big giant fin, which is your enemy in a crosswind. The rudder is good. So you use all the rudder just to cancel as much of the fin effect as you can, but you still have to do a lot of heroics on that crosswind decrab. Because this airplane has such little vertical side area, like the B-2, crosswind landings are just a dream, dirt simple. Maybe the opposite of what you instinctively would first think, but they turn out to have fabulous crosswind landing characteristics. Very low bank angle required to maintain a steady heading.
Similar question still in piloting. We have a pilot here that's asking, he can't wait to see JetStar come to successful fruition. I have seen from experience almost all aircraft being limited to high altitude airport performance. How is JetZero designed on that regard?
That's a great point. So hot and high, when the air density is thinner and the temperature is higher, I have limits in the combustor of the engine on the maximum temperature I can ever let it see. And if the air is thin, the wing can only do so much and the engine can only do so much. So it is interesting the ways in which the blended wing offers benefits across the board. What we're seeing is we have this benefit related to the landing gear once again. Because the landing gear is giving me this substantial takeoff field length savings, that means that we can go higher and hotter before we're at a comparable airplane's field length, even at sea level. Let me just think about this for just a moment. So as I said, compared to some aircraft, we have 40% shorter field length. This airplane has a field length under 7,000 feet compared to a 767. Some of them are over 10,000 feet at that takeoff weight. Some of them are in the high nines. So that benefit can be traded and spent on hot and high capability.
What materials are envisioned for the aircraft structure?
So the aircraft
composite,
structure, it will be composite, so that we don't have to have freezers and vacuum bags and autoclaves for doing resin transfer molding. So the airplane is built up in a dry form and put in the mold, and then the resin's injected. And of course, people who are familiar with that, it's a beautiful thing. Vacuum bagging with pre-pregs, strangely enough, causes the resin to become very porous because air's got to get out some way. When I heat it up, and whatever trapped air is in there's got to get out, and it makes billions and trillions of little pipes that go through the structure. And the industry's done a lot to minimize that. Resin transfer molding is very different in that it gives you extremely pristine resin for free. You just do the process, the air is already gone. It goes in and just fills the void. And so that problem is much improved. The other thing we're doing, though, is a thing, it's called stitching. So when you think about airplanes and how we assemble them, even a 787, You take the fuselage, which is made of all composite. I still got to drill and mount all the frames in the fuselage, nose to tail, drill that beautiful composite, put a hole in it, and mount it up. Wings are similar. As a top skin that's carbon, bottom skin that's carbon, ribs that are high-speed machined aluminum, front and rear spars. And then we go back and do aluminum processes again. We drill holes and put fasteners in. By the way, for those of you listening, did you ever wonder why airplanes are riveted? Where else in the world do we see the whole assembly process? Blue jeans, okay, blue jeans are riveted sometimes. But really, what is that? And the short answer is you can't weld thin aluminum. That's why rivets were invented. Otherwise, we'd be welding all this stuff, or at least we'd have that option. So one of the things that you have to accept when you do drilling and riveting is that you compromise the local structure, and you have to compensate with extra thickness and very careful margins on how close the rivets are and so forth. Well, that is only needed if I make separate pieces to be joined later. So what we're doing is we're sewing the airplane together with stitching first. So we're only investing the precision into the part at the very end when it's in a comprehensively precise condition inside a two-part mold. The volume is absolutely declared everywhere. No vacuum bags, no call plates. I fill it with resin. I will know exactly how much resin I need every single time. It'll come out the same weight every single time. And that stitching does two things. It means I don't have to drill holes to mount pieces together. I can create the mold with integral ribs and spars and everything. But also the stitching acts as a tear stop. So if I have damaged structure, and the FAA requires us to look at what's called two-bay crack, cut the skin away between two ribs and cut one stringer, or cut two stringers between two frames and make sure that the airplane can still take load. With that stitching, any crack that develops just stops at the stitch line. So it allows the airplane then to be lighter.
One more on the reduction, because you mentioned at the start of your presentation, you mentioned the reduction in stress from matching lift and weight.
Mm-hmm.
However, one pressurization loads dictate the skin thickness for most of the aircraft. And related to that, a thin tube with a very efficient pressure vessel, how much extra weight is added from a box pressure vessel?
Right. So that is true. The reason that airplanes are tubes is because they're pressure vessels. And when I pressurize them, I don't induce bending loads into that can. I only induce stretching loads, so-called hoop stress. So it stretches it fore aft, it stretches it left right, but that's simple. Nothing is being asked to bend. On our airplane, since we have a flat surface to start with, posts that hold those skins together, when I pressurize it, it wants to bend. It wants to make a little sine wave, right? So that is not the preferred way to go. You'd much rather have simple axial stress. What's interesting is that when you look at the blended wing, it has blended, obviously, the fuselage with the wing aerodynamically to make it give you the benefits of maximum lift and lift in general and control power to change your attitude. It's also blended the structure. So the bending load, so that skinny little bit of the wing outboard, going from the tip inboard is, I get more and more lift added and it wants to bend the whole thing. Even the middle part of the fuselage, it wants to be bent. But because the fuselage is so deep, those loads are quite minute in terms of bending. And when the structure that I put there to take the pressure loads more than addresses the bending loads. So if I only looked at pressure, our structure is like 15% heavier if I only had to take pressure loads compared to a cylinder. And it was hard to get to that level. But in fact, we don't see a penalty, we see a net benefit because we're doing so much of the wing with very long chords, allowing very high thicknesses, and now deep frames, deep structures that generate very minimal or saying it differently, can easily resist the bending and shear loads. And then they're asked to do pressurization. And when I size it for pressurization, I get most of the bending loads covered for free. Most of the airplane is minimum gauge, if you could believe that. You can't say that about many airplanes.
Two last questions, and really time is running out. Does JetZero feature include capability to be operated by single pilot, as airlines are looking to minimize costs operations?
So we are absolutely going to answer that bell if it gets wrong. So far, we haven't been asked about that, but it could very well happen. And many of us on this team have a long history in unmanned autonomous aircraft. We understand what that is all about. I've participated in a program where we had an airplane that we put a kit in to replace the pilot, robo-pilot. And so this is something that a lot of people are looking at, and it's pretty mature technology. Understand, though, that, of course, the certification of that and the other issues related to that, a lot of issues to deal with. We're not pacing ourselves based on that. We're running a two-man cockpit at the moment, but we stand ready if someone else needs it.
By the way, a pretty luxurious two-man cockpit, by the way, too.
Sure, it is. Yeah, it's got an MD-11 size. It's nice.
I'm sure they have more real estate than commercial jetliners. Yes, absolutely. All right. So finally, the personal question to Mark. Awesome job, Mark. How does it feel to see the product you've been working on for 3 decades coming to life?
It's an out-of-body experience. Up until we got this thing cooking, and I think we had flashover at the Paris Air Show. Warren, we can talk about where do we have flashover, where more people said, "Good Lord, this might be real," and they talked to their friends who also were saying that might be real, and then stuff happens, and things start to move. Prior to that, it's been a depressing path. It's been miserable. It's been totally miserable. Why? Because the capability is there. It's easy to demonstrate technically. It's been demonstrated thousands of times in hundreds of PhD thesis papers written. The whole world understands that there's a benefit there. The degree of the benefits in debate, but the benefit is significant, and there's nothing else out there that comes even close. We're talking about a 50% reduction or improvement in efficiency without new engines, without new carbon, using the same resins, using all the same 50% just from the airframe. Transonic truss brace wing is going to be a really cool program. That offers about 8% efficiency improvement. If you put better engines on, you get more. Same with us. Put better engines on, we'll get more too. So it's the biggest opportunity out there. And living decade after decade after decade, frankly, with the duopoly's silence about it, at best, and sometimes outright criticism of it, it's been hard. It's not fun, but it's been wonderful finding the team that I have found, and with the people who helped build this team to get us over that hump.
If it was easy, anybody would do it, by the way.
And
it's a testament to Mark's focus and desire and belief in the technology. It's the whole team, obviously, but Mark and the rest of the group that originally designed this airplane really truly believe that this is the right technology, and it's all of us advisors are also in that camp now, because we at first said, nah, that can't be. And then all of a sudden, once he started talking through it, like you just heard here today, it's pretty phenomenal. And it's an amazing technology that is going to change the world. And we want to be part of it.
Clearly Mark is one of those great aviation pioneers that sticks to it and perseveres, and I wish you luck, and I hope we get to see this flying machine soon, and I'll wish you all the success. But what's left is to thank you both very much for your time and explanation. This has been very, very educational for me, and as I knew about JetZero, but I knew very little. So Thank you very much for your time and all the deep insight. And thank you for all those that have been listening. And we look forward to meeting you in a future ISTAT Learning Lab. Thank you very much.
Good.
Thank you.
Thank you so much. Take care, everybody.
Bye-bye.
Bye.